Okay, here we are. Now, as you might have noticed already, this is really not a 2-hour robot. It is indeed a planar robot. Everything is in one plane. Of course, there is some thickness to the robot, but you can really imagine everything is everything is happening in one plane. But here, very clearly, you see there are 3 revolute joints. So there are 3 motors that that operate 3 different links. This is really not the same as a 2-hour robot, but what we can do is we can lock this 3rd joint and imagine this whole link to be a single link. So therefore, in effect, we have only 2 joints over here with 2 motors operating them. And as we just discussed, our assumption is any angle that we need here, we should be able to ask the motor to give us that angle, and the motor should be able to rotate to that angle. Now, if we can also note a couple of more things, the x-axis is here, y-axis is here, the origin is here. So when we defined q1 against a horizontal, it was really this angle respect to x. And when we said the second joint has angle q2, that's again relative to this horizontal, and this is an absolute angle. Now, why did I say this is unnatural for a robot? Because typically you are measuring at the joint, and the robot, or rather the motor, has no way of knowing where the inertially fixed x-axis is. So it is always measuring, so you would have guessed it already, it is always measuring a relative angle, which means it's measuring relative to where it started, how much it has rotated. So all your robot measurements, particularly at the other joints, at the base joint, usually it's not a problem because it's relative to a fixed base. So that is either you do relative or absolute, it's the same angle. But at the other joints, this can be a challenge. So keep track of relative angles and absolute angles, and we will talk about this later on. And in this case, just one last thing to note is that P over here is the end tip here, right? So when I say end effector coordinates, in this particular case, literally it's the point over here. If I now remove the robot here, so it's the x coordinate and y coordinate here that we are talking about. So in the first task, we want, no matter what the 2 motors are doing, we want to precisely calculate the end effector position. In the second task, given end effector desired position, we want to know what both these motors need to do to make the robot reach here. And in the third task, if I have a wall here and I want the robot to reach there and go apply a force, then I want to figure out what to tell the robot. Okay, let's go back to the theory and see how to solve this. Okay, back to the board. We had 3 tasks. First, let's start with the first task, where given arbitrary robot, or rather motor actions, we want to calculate the end tip position and velocity, and that, you might have guessed, it's relatively straightforward trigonometry. So we want to know what is x and what is y given q1, q2 and q1 dot and q2 dot, and we can apply trigonometry right away. And I believe all of you can do this in few seconds in your head already, right? So x coordinate of the end effector would be L1 cosine q1 plus L2 cosine q2. So L1 cosine q1 plus L2 cosine q2. And likewise, y coordinate would be L1 sine q1 plus L2 sine q2. And since we'll be seeing a lot of sines and cosines, we can use a shorthand notation to represent cosine and sine. So let's write this as L1 CQ1 meaning cosine of Q1, plus L2 CQ2, and the second y coordinate as L1 SQ1 plus L2 SQ2. That's it. It's as simple as that, end effector coordinates in terms of the joint angles. Now we can differentiate these to find the velocities. So we get x1 dot which is the x component of velocity of the end effector, that would be minus L1 SQ1 into Q1 dot minus L2 SQ2 into Q2 dot, and y dot would be similarly L1 CQ1 into Q1 dot plus L2 CQ2 into Q2 dot. And these together can help you calculate end effector position and velocity in just a couple of steps. Now what we would do, and you will see this is very useful as we go to more general robots, is try and write this in matrix form. So let's do this. So x1 dot and x dot and y dot, which are nothing but components of the velocity, or x and y components of the velocity of the end effector. Now I would write it as minus L1 SQ1 minus L2 SQ2, L1 CQ1 and L2 CQ2, the whole thing multiplied by Q1 dot Q2 dot. And let's call this equation 1 and let's call this equation 2. And as you would have noticed, this is a nice organization of the velocity relationship. What is happening here? Given how fast the motors are rotating, you can multiply it by some matrix. This matrix depends on the current configuration of the robot. In other words, the current joint angles Q1 and Q2. And when you multiply this out, you get the end effector velocities, right? And between 1 and 2, you can solve task 1. And there is a name for this. This is nothing but forward kinematics of a robot. And you can be a little bit more specific. This is forward position kinematics, and equation 2, where you are relating the velocities, is forward velocity kinematics. And why is it called forward kinematics? Because given motor actions, or motor motions rather, you can calculate what is happening at the end effector. And if you're doing position, it's position kinematics. If you're doing velocity, it's velocity kinematics. Great. So this is task 1. Now we have to talk about task 2, which is a little bit more involved. It's a little trickier than task 1. Ready?